Okay, so our next talk will be given by Michael Mahoney here at UC Berkeley on randomized numerical linear algebra, sampling for linear algebra, statistics, and optimization.
All right. Thank you, David. So what counts as foundations of data? So we've heard about sampling and sketching and the last day or two from one perspective. And a little bit of optimization today and tomorrow, and then some statistics tomorrow, and these sort of things. And so I thought I'd describe a little bit, at least in a sense, how to see how some of the pieces fit together. I think if you've seen some of these things, you see how the pieces fit together. But if you haven't, it might be a little bit dizzying, all the different things sort of going on. And sampling arises in a lot of different places. You can imagine there's a world out there, and you get data from the world and you put it here, and you want to make inferences about the world. I mean, that's one place sampling arises, so that's sort of sampling in statistics. A lot of what we've been talking about so far is sort of very different than that, right? There's 100 machines, and what you want to do is too expensive. And so I want to downsample and get a sketch. And so what, if anything, is the connection between those? And I think if your background is sort of in computer science or theoretical computer science, you tend to formulate problems and think about them one way. And that's rather different than if your background's in scientific computing or numerical analysis, how you formulate and parameterize problems. And that's rather different than if your sort of background's in machine learning or statistics. And these sort of ideas permeate through each of those areas. And so I thought I'd describe a little bit about what I think sort of makes these things work, sort of bridging some of the theory-practice gap connections. So I'll talk about that. And that's sort of in the context of this area, sort of randomized linear algebra. So a little bit of background and overview. If you thought about this is with the intent of boring you, so the first few slides will just sort of be a little bit of background, but to set stage. The first hour I'll talk a little bit about some sampling things, how they fit together, and then the second hour I'll get into a little bit more detail about a couple particular use cases. And so take a step back. So we wrote an article with Janaeus. I wrote an article with Janaeus in CACM a couple years ago, and so we did due diligence to sort of think about how this fit into the broader landscape. And I think that sort of matrices is a very natural way to model data. And a data model is something is natural in computer science, like databases, but less so elsewhere. But it's a way to model data, and it's perfect or imperfect, but it's a way to model data. So in particular, you have an m by n matrix and the m objects and n features, positive definite matrix encodes correlations and that sort of stuff. And so as hopefully by now, if you've been here the last day or two, there's a lot of sort of exciting developments motivated by a lot of large-scale data processing. Using randomization. And so historically it's sort of been assumed to be a property of the data, but meaning you measure it from the world, but you've seen it used sort of as an algorithmic resource or a computational resource. So what's the going on and what's the connection? So this randomized linear algebra, which is a theme of sort of what we've been talking about, arises because in a lot of cases you're modeling data as matrices, but you want to make inferential claims about the world, but you also want to compute on stuff. So this is an area that's interdisciplinary, as you may have gathered, and it uses randomization as a resource to extract insight from data, which means you need to understand these sort of two complementary aspects. So there's a very foundational perspective, right? The roots are in theoretical computer science. A lot of the techniques have connections with convex analysis and probability and metric embeddings and so on. And also sort of applied math and computational math and scientific computing. From implementations, it's not obvious, but well-engineered algorithms in this space, beat LAPACK in terms of wall clock time. That was the claim of the blend and pick result. And there's been a range of results sort of following up on that, using these things as preconditioners. And in terms of data analysis, strong connections with machine learning and statistics. So I think there's a couple ways to view about this, and sort of today and this week in the semester is viewing it sort of from the context of foundations of data. So how broad or how narrow is this in scope? So linear algebra sort of, as you know, sort of has a long history, and at least by the standards of the day, large-scale data analysis. So Gauss had this algorithm in roughly 01 for doing QR-type decompositions. Beginning of the next century, Hotelling and others developed PCA, and this was before computer science existed, right? So people think there's noise in the data, and you compute something. If there's noise in the data, then least squares residuals are good in certain senses. And keeping lead principal components might be good in other senses. And so that's sort of the motivation and what people have in the back of their mind when they're using this. And sort of having been sort of doing randomized linear algebra for all those, it seemed to be sort of an interesting sort of disconnect or change once you had the development of the computer. Because it wasn't obvious that you could invert a matrix on a machine stably, right? I mean, back in 1950, and so it was a big deal to get that done. And so I think culturally, a lot of scientific computing and linear algebra sort of pushed randomness out, and it entered into other areas. And so, so this, in a sense, is obvious, but I wanted to emphasize this because a lot of the particular questions people ask have remnants from this. And so what you're seeing today at this meeting and more generally is that people sort of are inventing and reinventing stuff that is grappling with some of these issues. And so early computer science and early applications of linear algebra focused on scientific computing problems. And there's this notion that you only want to solve well-posed problems. And so even for well-posed problems, certain algorithms might perform poorly. So that appears in numerical analysis, but it appears in statistics, right? You don't want to be solving poorly posed problems. They might not care about machine precision. They care about robustness and posedness in different senses. In early work, Turing may be known for the Turing machine, but if your background's in numerical analysis, you know that he and von Neumann and others had early work in numerical analysis where they addressed these very questions. And this led to sort of problem-specific complexity measures, sort of a condition number. So one notion of a condition number is the top-to-bottom eigenvalue. You saw a different notion of conditioning this morning for an optimization problem. So the point of a condition number is it's a problem-specific or an input-specific complexity measure that says how hard is this input for a specific class of algorithms. We'll get back to that. And the traditional condition number is how hard is this input for a class of iterative algorithms, like conjugate gradient or something. There was, for a range of reasons, sort of a split, and a lot of the continuous work moved on into applied math and scientific computing, and a lot of the discrete work went into computer science. You know, it's easy to formulate computation per se in discrete settings. You know, there's a range of sort of reasons for that. And so Ravi mentioned yesterday, you know, if you had asked a computer scientist 20 or 30 years ago which of these algorithms would perform well on scaled to data, you know, flow algorithms would or something, and that's exactly not what happened. And so with respect to what he was talking about yesterday, do you want to run an algorithm that gets all pairwise distances right? Is that better or worse than an algorithm that sort of gets them all right on average? And so this was the difference between random projections and SVD he talked about yesterday. And so one is obviously better if you view the world one way, and the other is obviously better if you view the world the other way. And so under the hood, and a lot of what we're talking about is trying to tease out which one's obviously better, and depending on the application, because if you're using method A versus B versus C, you're implicitly using one or the other. And so let's sort of characterize that. So so this goes into that in a little bit more detail. There's more information in these slides that I'm going to talk about sort of for archival reasons, but this will go into a little bit more detail about that. And so recently, as you may have gathered, there's sort of a convergence of these perspectives. And so I think this has been motivated by large-scale data, so scientific internet, a range of sort of applications. Computation per se is necessary. You need to do it, but it's not sufficient. Most downstream users of these things don't care about computation per se. And so if you formalize stuff in a particular model and you ask, is this tight or is this a lower bound, those are oftentimes very brittle to the detailed models of data access. And so they break if you consider something slightly different. And so most people want to gain insight in terms of downstream predictions. And so central to a lot of these developments is random sampling and linear algebra and randomized aspects of linear algebra. Where you have randomness, is it in the data or is it in the algorithm? Or is there a tension between the two? Maybe you can speed something up and do better because of some implicit statistical regularization. Continuous versus discrete, do you worry about numerical issues? And scientific versus business type sort of data motivations lead to very different types of questions you want to ask. So this is sort of a good hydrogen atom in a couple senses. I mean, one, a lot of the questions you might want to answer, you can ask much more simply in a linear algebraic setting, right? How do you talk about implicit regularization in a 57-layer neural network if you don't understand that for least squares? So a lot of the themes arise here, but also these sort of basic linear algebra things appear, but pulling them out and talking about them sort of in isolation oftentimes doesn't lead to the best insight about how they might be useful in a pipeline. And that pipeline could be use it as a preconditioner to solve some other linear algebra problem to high precision, but it could be feed it into an iterative algorithm or feed it into all sorts of other stuff or use it for statistical inference. So let's understand sampling in a range of these ways and view it sort of as a hydrogen atom to understand these sort of foundations more generally. So from that perspective, or with that background, sort of what have you been talking about for the last couple days? So basic sort of randomized linear algebra technique does the following. You have a data set. It's either in the world or on the machine. Most of what we've been talking about is on the machine. And you want to construct some sort of sketch. And that sketch is typically done by sampling something. It could be elements, could be rows and columns, but you sample something. And you use that sketch as a proxy. So you compute something on that sketch and you say it's good in some sense for the original problem I had. So that's the high level. And so if you take a step back, there's a million moving parts and a lot of projections and this and that. So I think the way to taxonomize it, to think about it, is in terms of basic design principles, right? If you wanted to have good coding practice or good theory practice. The idea is randomly sample. So matrices, what are matrices about? Are they about their elements or are they about their rows and columns? Some people would say that they're the rows and columns, right? If you have the row space and the column space, you're good. Others might say, if you have a term document matrix, I'm interested in this term in this document. If you have users and preferences, I'm interested in this user and this preference. So they're elements. So you either want to sample elements or you want to sample rows and columns. And in general, you want to do it in a data-dependent way, in a smart or careful way. And then you use that as a sketch to chew things. But doing that sort of naively, or doing that uniformly typically does suboptimally, so use it in a data-dependent way. But typically a naive way to compute the data-dependent structures you want, that's going to be expensive. And so you can approximate them, and you heard about approximating leverage scores, or you can pre-process or precondition. So preconditioning is a notion that doesn't appear so much in computer science, but it's very common in numerical analysis. And the idea of preconditioning is I have a problem, and I transform it to a different problem. I solve this problem, the two solutions are the same or easily related to each other. Right? And so one answer is I transform it by doing an identity transformation, in which case this is no easier than this, right? Another is I transform it by computing the exact solution, in which case you've done a lot of work to transformation. So the question is there a trade-off space? Can I transform it in a way that's quick and also such that I can solve this more quickly? And so that is what random projections are doing in this case. They rotate you to a random basis where good things happen. And so I'll give you some examples of that. But I think that's the way to think about a lot of these random projections and how they're being used. So if you do element-wise sampling, you're thinking of the matrix as a bunch of numbers. And you sample uniformly or not over the numbers. And what does that mean? That could mean the data's here and I pull out a few things. It could mean, I don't know if it was Ravi or someone yesterday mentioned 2 techniques, 1 method. It could mean there's a world out there and I'm a company, I want to measure, do you have a preference for this or that? And so I show you something, and if you click or not, I sort of assume that you have a preference for this. And so it could mean that I sort of interrogate the hypothesized matrix. Uniform sampling tends to lead to poor results. One thing that's been used a lot is non-uniform sampling with respect to the magnitudes of the elements. So this is the element-wise analog of the row norm sampling. So it's an L2 on the elements. And if you do that, you tend to get bounds of the following form. So this is a spectral norm bound, A minus the sampled version in spectral norm. This isn't true element-wise, but in terms of the directions of variance. That's better than something times a scale. If you have this, then you're going to get additive error bounds. And so additive error bounds, yesterday you heard, were bounds of the form I'm better than best plus epsilon times some scale, where that scale could be large or small, right? And so if you're asking for something very fine and that scale is huge, you might as well return nothing, right? I mean, because you're not going to say anything. If that scale is pretty small, then you might be saying something. So it'll give you additive error bounds, which are good but not great. And the proof method uses ideas from random matrix theory, if you're familiar with this. So a different thing is to sample rows and columns. And we've seen a lot of this. And again, uniform sampling may perform poorly. Non-uniform sampling does better. So if you perform non-uniform sampling according to row lengths, this is what we've seen a couple times yesterday, you again get a matrix multiplication result of this form. And if you get this result, this is a primitive we'll get back to, but if you have that result, again, for low rank approximation and a range of other things, you get additive error bounds. Right? So you are as good as the best rank k that SVD gives you plus epsilon times something large. And that something large is here. If you sampled uniformly, that something large would be the dimension, or the dimension squared. But you want that something large depends on the norm. So is that good or not? If you're exactly rank k, if you're well approximated by low rank, that's not reflected here. If the overall mass of the matrix isn't too large, that might be reflected. So, and here the basic proof method is you look at expectations and variances and more sophisticated things for spectral norms. So when we first saw this was a little bit funny because you're not doing anything better by looking at rows and columns and elements, and you feel like you should because you're capturing subspace structure. And so what can you do? And so a different thing you can do than the norm squared sampling is use this leverage score sampling. So this is something that originally I guess Janaeus and I sort of reverse engineered, and then it turned out it had this interpretation. And this is looking at row norms of left singular vectors, which is equivalently diagonal elements of projection matrices. And I think the way to think about it is it's relatively easy to normalize rows and columns, right? You just normalize them. It's a little bit harder to normalize away the subspace structure, right? So if there's an example of a problem, where you look like this, and I ask you which data point's going to have the biggest fit. I mean, any metric that's reasonable is going to find this one, right? So this is one way, leverage is one way to capture that. Now, do you want to find this or not? Do you want to sample this or not?
It depends.
It depends. If you're a statistician, you may give a very different answer than if you're a computer scientist. But if you're a computer scientist and you're making a claim about what's sitting in front of you, there's no world. You're making a claim about what's sitting in front of you. You're an algorithm. There's an input, there's an output. You better be right. Garbage in, garbage out. You better be right. So you want to find that. If you're a statistician, you might say, geez, that's an outlier. That's something funny, and I want to not find that. And the empirical questions, maybe data look funny, and you're using least squares because there's nothing else that you can use. But so you want to bias yourself towards funny things. And a lot of the early work in theoretical computer science, because it's asking algorithmic questions in computer science, biases you towards that. And you may want to bias away from that. So they're useful in regression diagnostics to identify outliers. Like most things, you can be naive in their computation or not. To compute them exactly takes QR time or something like that, as you've heard. You can compute them a number of different ways, and you heard about one way in essentially random projection time. So the time it takes to implement a projection, you can approximate them. There's a couple different notions of approximation. As a practical matter, in terms of use cases, you want to find large ones and small ones. To first approximation don't matter. We'll get back in the second hour to a case where they do, but you can usually easily take care of that. And you saw an example of this in the optimization talk this morning. Replace the non-uniformity, which is a variant of this, with half non-uniformity plus half uniform. That means nothing's too small. And so that's why she did that. And there was a question about, does this correspond to regularization? And it does in a very natural sense. The other reason this was sort of interest is that it provides a data-aware subspace embedding, meaning I look at the data, I know something about the data, but I get an embedding, which I'm saying, if I have a rectangular orthogonal matrix, then if I'm tall, then I know that like this, that's an identity, right? I want to say that the sampled version of that is roughly an identity. And the way to quantify that is to say that this minus wherever the spectral norm is the largest singular value, they're all 1 if they're all between a half and 3/2. So I could place that with an epsilon. I want to say strictly away from 0. Why? Because if I parameterize problems in a worst case sense, I'm dead if I don't accomplish that. In other use cases, it might be fine to violate that, and we'll see that. But it gives you data-aware subspace embedding. So from the perspective of theoretical computer science, you heard, I think it was yesterday, this should be thought about as a subspace analog of Johnson-Lindenstrass. Right? Johnson-Lindenstrass is about a discrete point set, but if you put a ball, a unit ball on the low-dimensional subspace, this is a subspace analog of Johnson-Lindenstrass. Numerical analysts would actually think of it a very different way. They'd say this is an acute perturbation. Right? It's a perturbation that zeroes out most of the canonical axes, most of the columns, such that you don't lose rank. Acute means it's less than 90 degrees. So you rotate a little bit, you zero out most things, but you don't lose rank. And this is one way to think about it. This is a much more geometric way to think about it. And so neither is incorrect, both are the case, and one or the other is more useful in certain use cases. Now, norms of columns and elements are not too hard. These take a bit more work, even if it's random projection time. And so depending on your use case, you may want to precondition. So is this a good thing or not? And so look at numerical analysis book. There's a range of methods, and it depends on the problem, it depends on the input, it depends on the data presentation, it depends on a lot of things. And so similarly here. So the main challenge for a lot of these things is that you want to find these outlying things, you want to find these interesting things, so you can find them or approximate them, or you can just say, I don't care because I want to solve this downstream thing, the least squares problem or something else. And so what I'm going to do is pre-process or precondition my input. And so the main challenge for uniform sampling is that there might be one or a small number of coordinates that are particularly important. There might be this guy. There might be, I think someone put up a 1, -1, 1, 1, 1, 1, 1, 1 sort of example, right? You got to find that guy. So think of this as a delta function, right? There's this one coordinate out of n that's important. How are you going to pre-process a delta function? You hit it with a Fourier transform and it spreads it out to be a sinusoid. So Hadamard transforms, Gaussian random projections, count sketches. All of these things essentially rotate you to a random basis where these things are uniform, where the leverage scores are uniform. All right, so why they work in a lot of ways is because in the randomly rotated basis, they're uniformized. Only approximately, right? So Ken was talking this morning, they're uniformized up to a factor of 2 or 10. I mean, in that case, they could be uniformized only up to a factor of log n, and that's sufficient for what you want to do downstream. So but they're uniformized. Should you ask for the constant factor or the log n? This is a preconditioner, right? Depends on that trade-off point you're interested in. So you should think of it that way, I think. All right, so that was a little bit of background. Let me pause for a second because I want to go through in a little bit of detail the matrix multiplication and how this is used in the least squares case, but maybe pause. I forgot to bring a water, so I'll be okay. But is there any questions? So hopefully this was a review and maybe shed light on some of the things we've been talking about, and at least didn't make it unclear and hopefully clarify it a little bit, at least to some people. Yeah.
You have a pretty general definition of preconditioner. Would you describe sketch and solve as preconditioning?
Yeah, so I don't know how general you want to be. Let me get back to that after the least, ask that question after the least squares sketch. It could be, but then there's a precision issue. If you want low precision, it could be, because according to what I just said, the random projection would precondition, and then you sample uniformly. So for the class of sampling matrices, this is a preconditioner for that. And you're not going to get high precision because of the 1 over epsilon and 1 over epsilon squared, but you'll get low precision, so it would be. Yeah, so if you want a high precision, you got to couple this with a more traditional preconditioner, which is the way they were used. David was talking about it yesterday, where you'd take this low precision thing and then feed it to a more traditional high precision. But within the context of sampling algorithms, it is, yeah. All right. And so that question leads me into a couple things. Actually, not the first thing. I don't know if you can see this. I can see it on my screen. But the first thing is talking about matrix multiplication and then least squares. So, how do you, so sort of a primitive in all of these things, I think, and you saw one example of with the subspace embedding, is matrix multiplication, right? So what could be simpler than this? So given an m by n matrix, say they're all in size n. So given an n by n matrix and an m by p matrix B, approximate the product. And I think that when most people, at least initially, see matrix multiplication, they think of it in the following way. I have a matrix A and a matrix B, and it's defined matrix multiplication is a transformation, it's a function, right? It's not a bunch of elements, but it's defined operationally in terms of elements to say that AB, ij is a sum over k of what? Of A, I, k, B, k, j, right? Meaning it's a column of A and a row of whatever. A row of A and a column of B. So that's not untrue. Think of it this way, though. AB is a sum of outer products. All right, so you either block by rows or block by columns. If you block A up by columns, block B up by rows, you have a dot product, each element of which is a rank 1 matrix. So think of it this way, and if you're dealing with rank 1 matrices, these are objects. If you're dealing with numbers, these are other objects. And if you're summing over 1 to a million of them, you might say sampling will work. Right? And so that's what's going on under the hood here. And so think of it as a sum of outer products. Now, don't think of it naively this way, because you might not access the data this way, but this is sort of what's going on under the hood, I think. And so the sampling approach basically says, fix some set of probabilities, whatever you want. It could be what we're talking about. You'll see in the second hour, it could be other thing. And for t equals 1 to c, sometimes this is an s or an r or an m or an m sub j. I mean, it's the number of samples you're drawing. Choose a rank 1 component, but clearly don't write it out naively. Choose a column of A and a row of B with those probabilities. And so approximate the product AB. This is whatever, k is equal to 1 to n, if it's m by n and n by p, and say that this is close to a sum from k equals 1 to c of a scaled version. All right. You got to scale by that, because if I'm estimating the sum of a million numbers by sampling 10 or 100 of them, I got to scale by a million over 10, right? So this is a non-uniform analog of that, just to get estimators to work. So the same algorithm written as in matrix notation, pick a bunch of columns of A and rows of B, and write it as an outer product that you feed yourself through some low dimension. If you have this, you can think of this as a sampling matrix where this has one non-zero per row. And once you write it this way, you could say, well, what about other matrices, right? You're starting to decouple the linear algebra from the algorithmic properties. And then you can say, what if I had other sort of types of things? But for right now, think of that as a sampling matrix. So if you do that, so there's simple and there's hard things, right? So I'm trying to describe some simple things. And if you do what I just said, the following is simple in the sense that if you know means and variances, you can prove the following. So for any set of sampling probabilities CR equals AB, element-wise, just write out a sum. And it's for any set of probabilities, this is equal to the variance. It's something minus a second term, which you usually drop if you're doing bounds. All right? That's just write down means and variances, nothing fancy. And so from these, it's easy to say that the expectation of AB minus CR Frobenius squared, but you can pull that off, is the sum of these things, right? So you can get a bound on that. You can remove expectation with Markov's inequality or Martingale's and a range of other methods, which are sort of you've heard about and are sort of more standard, but a little bit more complicated. You could ask, what's the set of probabilities that optimizes this? Why this? Because it's a convenient thing, not because it's the most important, but we'll see this is a useful primitive for a range of other things. The probabilities that optimize that. So that's a reasonable notion, not the perfect one, but a reasonable notion of quality. The probabilities that optimize that are this. So a norm of A and a norm of B. Now if B happens to be A transpose, this is a norm squared, right? Divided by a Frobenius norm. So these are the optimal probabilities. If you use that, then AB minus CR, the Frobenius norm of that, is less than 1 over root C. This is the usual 1 over root C that you get in a Monte Carlo method, times the scale factor, which is norm of A times norm of B. And so in particular, if B is equal to A transpose, you're saying AA transpose, which is the form we've seen a bunch of, minus, call it CC transpose, is less than 1 over root number of samples times the norm of the matrix squared. And this is very robust. If you approximate this in any number of ways, it works. You got to find the large things. You can miss small things. If you're off by a factor of 2, you got to oversample by a factor of 2 in worst case, but in practice you'll do a lot better. So they're very robust in a sense. What is this thing? This thing is a complicated way of writing the spectral norm of that thing. Right? This is a rank 1 component. So if I'm summing numbers, I'm going to say, using any probabilities, I'm going to get a good expectation. But if I bias myself towards large numbers, I'm going to get a good variance. And so that's what this is saying. So bias myself towards large things, large matrices. This is the matrix analog of that. If you estimate the height of people, it doesn't matter. You choose, everyone's about 6 feet. You choose a few hundred people, you have a good estimate. If you try and estimate wealth or something like that has a huge range, you better bias yourself in a better way. So that's all we're saying here. Bias yourself towards larger things. All right? That's Frobenius norms. Think of a matrix multiplication as a primitive that you'd feed other things into. And so for a lot of things, you can use Frobenius norms. You might need a spectral norm, but a spectral norm is less than a Frobenius norm, so you could bound it that way. It's going to be suboptimal, but you could. You can use more direct methods, so there's a range of ways to do this, here's one result. If you make the spectral norm small and the Frobenius norm not too large, I'm saying they're not important here, but the previous result holds for anything. This thing holds for a subset of matrices. It holds for matrices that you're going to be interested in, that have spectral structure where something decays, but it's a subset of matrices. If you sample with a complexity that's slightly more complicated looking, but will be better in practice, then the spectral norm AA transpose minus CC transpose can be less than epsilon. So I'll say why this matters and how this is related to the previous thing, but I wrote them in 2 different ways just to highlight something. And so the reason why this is a primitive that's interesting to feed into a lot of things is, so matrix multiplication is going to be the primitive for a bunch of things, and you use better and worse bounds for sampling, for projection, for whatever. Here's the 90, I don't know if it's 99, but 95 or 98% use case. So spectral norm bound is better, in the sense we'll get to here. but it's less general in the sense that it holds for B equals A transpose. It doesn't hold for arbitrary A because of those two conditions. Basically, you need to have a relatively low soft rank. And so better results in matrix multiplication propagate to a lot of downstream things. And so we're talking about here the sampling case. The same is going to be true on the projection case, and you heard a bunch about that. So the main use case for the spectral norm bound is the following. I have a matrix A, which, getting the letters right is always a mess. So this is consistent with the previous page, but a lot of other talks and so on. So now I'm calling it A transpose. But let this be a tall orthogonal matrix. Namely, let it be this thing. And what I want to say is that U transpose U is an identity. And I want the sampled version of U transpose U to be roughly an identity. And a way to quantify that is to say that all the eigenvalues of the sampled version of U transpose U are close to 1. So meaning the spectral norm, the largest deviation, 1 minus this is less than a half. In order to do that, I can use the result, the Frobenius norm result I had 2 slides ago, to say that the spectral norm is less than the Frobenius norm. The Frobenius norm is 1 over root C times the norm of A. But A here is an orthogonal matrix. So the Frobenius norm of U. What's the Frobenius norm of an orthogonal matrix? I have a tall matrix. It's 1,000,000 by 10 orthogonal columns. Am I standing in the way, or is the answer still up? I don't know if you get to see it. So if you have an orthogonal matrix, the Frobenius norm, the sum of the leverage scores is low dimension. It's 10. It's not 1,000. So the reason this is of interest as opposed to the additive scale factors is that if you sum from 1 to n, more or less anything, you're going to get something like n, unless you have some structure here. And so the reason the leverage works is because the sum is 10. More generally, what if it's 11? You try and generalize this to other problems, to other objectives. If the sum of the leverage or influence or sensitivity, these generalizations, is low dimension or low dimension squared, then you can typically take advantage of it. If it's high dimension or root high dimension, you got to eat that in general. So that's why this works. So you say that the Frobenius norm squared is d, the low dimension, divided by root c. That's going to be a problem because that should be probably d squared. D. So this should be a square root of d, I guess. Yeah, this should be a square root of d. Meaning that if I want to make this less than a half, c needs to be d squared over 2 or something, right? And that d squared is going to appear everywhere, right? When we're doing QR, it's high dimension, low dimension squared. If we need the number of samples to be d squared, that's going to propagate down. If we can make it less than that, we're going to win. And so the way you win is by looking at a spectral norm bound directly. The thing I had on the previous slide, if you instantiate, it's going to be something like log c over c times a Frobenius norm times a spectral norm. That should be root d, not d. What's the spectral norm of an orthogonal matrix? It's 1. So it's root d times 1 over root c times the log factor. And so I'll be able to use a matrix multiplication primitive. I could use a Frobenius norm. It boils down to matrix multiplication, but that's suboptimal. If I use a spectral norm directly, then I'm going to need c to be d over epsilon up to log factor. So this is where the win is. And that's true in the data aware case, the data oblivious case. That's going to be true everywhere. What if instead of having a sampling matrix where I have 1 non-zero per row, I have 2 non-zeros per row, or n non-zeros per row, where the n non-zeros are Gaussians or Hadamards or Rademachers or any of all the same to first order. To second of order, there's log differences, right? But to first order, lots and lots of dense sampling matrices. From a theoretical computer science perspective, there's a natural interpretation in terms of Johnson, Lindenstrass, and a random projection. And the subspace embeddings, as I said, can be viewed as a sort of vector space generalization of that. And in linear algebra, you're thinking of it as a rotation, roughly an orthogonal transformation. The randomized Hadamard is exactly an orthogonal transformation. The other ones are approximately. And natural interpretation in terms of preconditioning or pre-processing. So I'll get to that in a second. And so this is to hopefully this was clear by now, but to relate back to what we were hearing about earlier, subspace embedding is that I preserve the geometry. So this is the expression. If you remember the definition of a spectral norm, right? A spectral norm is the largest direction that a unit length vector gets stretched. You can write it as whatever, as max, ux over unit length x. That's what this is. So with the expression we saw before is exactly this, which is exactly this. Lots and lots of constructions. Some of them, I've described the data-aware ones, bias yourself towards important things. There's lots and lots of data oblivious. So this was first used in the data-aware context. It actually predated the randomized, the fast randomized, the Alliance-Chazelle result. Then Sarlos coupled this with the Alliance-Shell result, and there's been a lot of follow-up in a data-oblivious way. So you want to use a result in this area. Should you use a projection or should you use a sampling method?
What was the first part of your question?
If you're going to use a result that we're talking about here, should I suggest to use a projection method or a sampling method? So I don't have a suggestion. It depends on you and your problem. For certain problems, sampling is more natural. For other problems, projections will be better. But they're going to boil down to the same thing under the hood. So think of it that way. As I said, this is an acute perturbation, meaning it's a small rotation from 1,000,000 dimensions down to 10, where I zero out, not to 10, to 20, to 10 log 10 or whatever. I zero out most of the entries, but I don't lose rank in particular. So one of the points is, this is sort of a must-have if you view things from a computer science perspective. You need this. In a lot of ways, it's good to have, or it's good to have something related to this, but you can relax on this. What if you lose 1 or 2 dimensions? Is that the end of the world? So I'll give an example of the answer to that. What if you want to do something statistical where there's a bias variance trade-off? So how would this generalize in those cases? So I'm going to give the least squares example, but let me pause and see if there's any questions or violent objections or violent questions or non-violent objections.
Where did you talk about data oblivious? Like the whole thing was looking at...
So I didn't talk about it because I was able to backward point to everyone else. So if you have a dense sampling matrix, so the reason you need to sample is if I just choose one thing, I need to find this one outlying thing. If my sampling matrix is dense, meaning I have a plus or minus 1 in every entry, or if I have a Gaussian in every entry, or if I have something else, if I make this, quote, sampling matrix dense, it's not a sampling matrix. It's sampling a linear combination of things, which is a random projection. And so the count sketch is a very structured way to do it that allows you to get extremely sparse. The randomized Hadamard is a way to do it that has a hierarchical structure, so you can implement it with fast Fourier techniques. I mean, Gaussians have other... So when you make this dense, but the reason it's nice to distill this out is to first order exactly the same analysis works if you sample in a smart way, if you do data oblivious projections, if you do any of a range of things. This is a structural thing you need to satisfy. And so should you do it in a data oblivious way or should you do it in a data aware way? And so the answer is the same as it depends on the context. All right. So least squares. So I like least squares because every time we get a new result, you realize you didn't quite understand something about what was going on. And so, again, dwell on this. We've been talking about this, but so this has been something that's been studied forever, right? But I mean, we're looking at it in a new light. And so think of it where I'll describe some stuff you've heard in the last day or two in a way that complements. I mean, so if some of the previous talks had emphasized numerical things, I would have taken the counterpoint and described that, the complementary sort of TCS approach. So think of this as in light of that, but also distill out structural properties like matrix multiplication and where that might be used there. So think of this as a test case for saying, how would matrix multiplication be used here? So least squares minimize ax minus b. And now we're m by n, I guess. And so in a RAM model, this actually is, a far from perfect guide to practice even on a single machine. But it's high dimension times low dimension squared time. I should point out the other reason to distill out the structural properties is what, if anything, that we're talking about here ports to a distributed data center. Right, if you distill out the structural properties, you can deal with that separately from RAM and other issues and ask statistical questions. You can ask different questions, whereas if you don't distill that out, it's just much harder to figure out what's going on. So for least squares is a nice example here because it uses these techniques and you get the best results. And you get the best results for very different and rather sort of inconsistent metrics. But you need to use the sort of basic method in somewhat different ways. So if you want the the algorithm that in terms of worst case RAM, running time in RAM, beats the algorithm Gauss had from 01, an algorithm here will do that. So you can use randomized Hadamards, and then depending on aspect ratios, you can use NNZ type methods. It's not obvious that if you can make a statement like that, that the method has anything to do with something that would perform well numerically. It turns out you can beat LAPACK in wall clock time, and then when Blendenpick did that, LAPACK responded, and then there was an arms race. So I don't know what the state of the art is right now, but you can compute things, you can use these methods and feed them into low rank approximations and get PCA on 50 terabytes of data, 30 terabytes of data sort of thing. And the underlying embeddings and approximation techniques are the same, but clearly the way it implemented is going to be very different. And it's useful in a range of data applications, and sometimes it's useful for very different reasons, right? It's useful not because we squeeze the last little bit out in objective, but there might be implicit regularization, right? If you're using sampling, the noise inside the algorithm might synergize well or poorly with noise in the generative processing of the data. So least squares. And so there's two notions of conditioning here. So this slide hopefully is a review by now. One is sort of for low precision solutions, you need to capture something about the non-uniformity on the canonical axes. And for high precision solutions, you need to capture something about the aspect ratio of the quadratic well that's sort of implicitly there. Condition number is the ratio of max to min eigenvalue. It captures the one. Non-uniformity on leverage or influence or sensitivity scores, either the max to the min or the max to the average, depending on the exact objective you care about, is a condition number for a class of sampling algorithms. These have to do with eigenvectors. These have to do with eigenvalues. They're just different. In real cases, generative processes of the data, sometimes they're correlated, especially on extreme eigenvalues and eigenvectors. But in general, they could be whatever. These are for L1 norms as generalization. L2 norms as generalization for L1 norms. You heard this morning a variant of these for an iterative first order type optimization algorithm. So that's not exactly this, but it's a first cousin of this in the context of an iterative optimization algorithm. So here's the basic least squares algorithm. Compute this non-uniformity structure. Randomly sample a small number of constraints to it, and then solve the subproblem. So this is sketch and solve. Give me a sketch, solve. A naive version, I'm the one of these M's. I like this result because it's a core of a lot of things, but it gives you worse than the exact answer. It may fail with some probability delta, and its running time is worse. So that doesn't seem to suggest much for it, but in fact, all of those can be taken care of. So a non-naive version, as I said, is the best worst case algorithms and good for all sorts of other things. So let's understand what's going on here. And that picture here is just this picture. Find an outlier. This is either the genome research or the PNAS paper. So the genome research paper, we looked at some stuff in genetics. The PNAS, we looked at something else. Question, how uniform or not are these? Is this correlated at all with something that might appear in practice? And so what you have here is SNPs. SNPs are single nucleotide polymorphisms, the single positions in the DNA where you're going to have some difference between people. And the y-axis here is a notion of leverage. This is a low-rank approximation, a generalization we've been talking about. And the things that stick up are flagged as that's higher leverage than that. Now, if you ask a geneticist, what are the important SNPs here? And say, give me the 50 most important SNPs. They have certain metrics. One is called informativeness. It's related to mutual information. They'll tag these, the ones in red. So there's a strong correlation here. And this is not a one-off, but it's probably a 50 off. So there's lots and lots of examples where the non-uniformity structure you see in very real data looks something like this. So you might say, why is this? If you're using an L2 metric, shouldn't you use an L3 or some other metric, right? And the answer is people do least squares, and people do PCA, and people do all sorts of things like this, not because they really believe the generative processes are Gaussian, but because that's something that they can compute and scale and so on, right? And so looking for outliers, that could be a mistake. You kicked your machine. That could also be an outlier that's the most interesting SNP relative to a model that you know is wrong, but you're using for convenience. And so this is a very common thing. So these things are outlying. So I remember we were working with some people up the hill at LBL, and they applied our method on some mass spec data, and it returned garbage. And they went and complained and said, your method didn't work. And I said, what do you mean it didn't work? And he said, it returned garbage. And I said, how did you clean up the data? He said, we cleaned it up. Show me the garbage. And of course, it was all artifacts of experiment, the experimental setup. That didn't matter for the things they were using, but that if we have a method that finds those, found those. I said, why don't you just remove all those, run the algorithm again. You found these things that you failed to clean up before, that's fine. Run the algorithm again, and then it zoomed in exactly on the outlying things that they were interested in. So again, should you bias yourself towards these or use these to filter the data? All right, so maybe I'll just have one question I'll ask for the next hour. All right, so it depends. It depends on the use case. I won't promise. Maybe there'll be a different question coming up soon. But so this is the way to think about this. This is just a structural result. If you're modeling data as a matrix in a Hilbert space or Euclidean space, this is just a very basic structural result. I mean, for L2 objectives, it is not possible for every data point to have a big influence on the least squares fit. That's what it means if the sum of the leverage scores is small. In theoretical computer science, and I'll go into this in more or less detail in the next hour depending on time, but you can invent objectives. There's lots of objectives. And for some of those objectives, the sum of the sensitivities is small. You can use sampling techniques. For other of those objectives, the sum of the sensitivities is the high dimension. You can't use sampling techniques, at least not in worst case. Of course, you can regularize and do lots of other rigmarole, but that's the leading order bit. So for these objectives, it can't be the case that every data point is important. And so that's why sampling would work. All right, so there's a sketch and solve. So we can make this algorithm fast by running in RAM. We can make it high precision. So how do you make it fast? Use a Hadamard method. Use a count set sketch method. Use any of a range of methods we've been talking about. Or compute fast approximations to the leverage scores. How? We saw this morning, you have your matrix A. I won't use a QR inverse and I won't use a UR. I was talking to Michael Saunders before the talk. He was complaining about UR. I'll use a QR. So A, is equal to QR. That's expensive to compute. Let's work on pi A. What is that? This is anything. But in particular, it's a Hadamard-based projection. Gaussianist, if you like that. It's a count sketch. Let's say pi A is equal to Q hat R hat. That's exactly orthogonal. That's perfect. Numerical issues and whatever. But that's perfect for that. In particular, if you were to look at pi A R inverse, you have an orthogonal matrix. Apply it up here. A R inverse, this is equal to Q hat hat. That's not orthogonal, but it is the right dimensions, and it's close to orthogonal. In what sense is it close to orthogonal? In the sense that Q transpose Q minus Q hat hat transpose Q hat hat, spectral norm, so in this matrix multiplication sense. All right, and there, you need to wedge an extra projection in there to make things fast and so on. But that's the structure that makes that work. And you can make it high precision. So you heard yesterday about one way to do this. A different way is to call LSQR, which is conjugate gradient of the normal equation, sort of done right so you don't mess up condition numbers. And if you have any questions about that, I'll pass the buck to Michael Saunders, who can probably answer it in more detail. So if you're interested in that sort of stuff, call that as a black box, because that's been stress tested for 30 years. Although now there's RM or LSMR. So I'll give a plug to LSMR, which is a new. But call that black box. And how are you going to do that? So I'm saying you're preconditioning here. You could take this wherever. If I'm solving AX minus B, pre-multiply not by Q transpose, but by Q hat hat transpose. Call LSMR. So what makes all this work? AX minus B. There's a solution, AX opt. So this is clean because you can write it in a nice clean form. The iterative algorithms are a little bit more complicated because you can't write that in a nice clean form, so you need to do something iterative. As well as the preconditioned version. So now I slipped in a new letter. That's an S or maybe a pi, but this is just your sketching matrix. So here's the basic structural result. If sigma min, so we know that the eigenvalues of U, singular values of U are 1. If sigma min of the sketched version of U is greater than a half, you can actually be bad on the upside, but say it's less. Let's say it's between a half and 3/2. And if UA dotted into B perp, what's B perp? B perp is the part of B sitting outside the column space of A. So UA dotted into B perp is 0. If UA dotted into B perp when you sample it is close to 0, less than epsilon times a scale, where this scale is the thing, there's a number you're computing here. If this is true, then your relative error. You plug your solution back in, ax minus b, you're 1 plus epsilon, good. But with the difference between the two norms, you 1 plus epsilon, good. There's a condition number factor there, of course. So this is a structural result. There's no randomness in this statement. All right, and so this was the original result when we first had the relative error result. And there's no randomness in the statement. So you could use the left singular vectors as omega. I mean, maybe not quick to compute them, but you could. You could use any matrix you want. You could run an algorithm and you could check these conditions after the fact. So it just so happens that if you use leverage sampling, or if you use random projections, or if you guarantee you have a subspace embedding, you satisfy these in a sense that computer scientists like. Worst case, a priori bounds. But you could run something and fail to satisfy the worst case a priori bounds, but ask, can I certify that these are true? And so, this is a structure result. There's no randomness here. And both conditions are approximate matrix multiplication, right? The first one, eigenvalues are 1. I want the sampled versions to be close to 1. And the second one, that's 0, right? So the second one is an approximate matrix multiplication result. Here you don't need the high probabilities and all that rigmarole. This is sufficient, but you could do that if you wanted. All right? Lots of constructions satisfy this. Heavy hitters, I mean, there's frequent items, I mean, there's things. The analysis sometimes isn't presented this way, but you can feed it through a result like this, and this is sort of the basic structural result to get least squares approximations. If you're interested in the data in front of you, the data on the machine. If you're interested in the world, we'll get to that later. But this is sort of the basic structural result. And I used to worry about this, but I'd say be a little cavalier about the epsilons. Theoretically, in theoretical computer science, you tend not to care about it. And numerical people precondition. They used to, early work here, they used to worry about it a lot, and this used to be a big sort of point of criticism. But set epsilon to be a half, you have a good preconditioner. And you take 2 extra iterations or something, right? So there's a trade-off point. You could make it 1 over 100, but set it to be a half. And machine learning and data analysis is just different pain points. And here's the plots for blend and pick that says, you can beat LAPAC. Something that I learned here that probably should have been obvious, but I didn't know prior to this. So a subspace embedding is sufficient to get a good preconditioner. But is it overkill? All right. What if, in random matrix theory, people look at the spectra of random matrices and they look at the tails, and you might ask, could I get greedier? Could I sample a lot less than the d over epsilon and log factors? Go to 10d. So if you do that, you'll fail in worst case. So, we know that. And it may be the case that on any particular input you fail. So if I want to do sketch and solve, that's a problem. Because maybe I failed to find the one thing I want. If I'm going to use that as a preconditioner, that's not such a problem. And basically the reason is that if you're going to use this and you're going to say this is a good preconditioner, and you're going to call a black box, what if I have something else that's a rank 1 perturbation of a good preconditioner? Because I lost 1 dimension, or a rank 3 perturbation of a good preconditioner, because I lost 3 dimensions. I need to do 3 extra iterations or something, right? So just a few extra iterations. So you can get much greedier on the downsampling step if you're using it in a pipeline. The simplest version of that is an iterative least squares solver, but there's many other examples of that. All right? Yeah?
So how big is this performance gap on a GPU?
That I don't know. You'll probably hear tomorrow in this context of second order optimization, which uses these things and generalizations of these ideas about a GPU implementation. So I don't know the answer. We just don't have the implementation of the straightforward least squares on the GPU. It probably wouldn't be too hard. But this is a few years old, and the LSRN, which is the extension of this to use random bits with Gaussian matrices, was also a few years ago. So I don't know. Yeah, I don't know how it would perform on a GPU. Good question if someone's numerically inclined. It's low. It's actually a very low-hanging fruit. All the infrastructure's in place, so we would know how to set that up easily. But I don't know. I don't know. All right. So going through matrix multiplication, because feel like if you see that and how that relates to theoretical computer science objectives like Johnson, Lindenstrass, where I want to get every pairwise thing, and if I lose a dimension or two, how it's used. So I wanted to go through the matrix multiplication primitive, then go through the least squares primitive, and then wave my hands and say, sort of it all boils down to that, which is a bit of an oversimplification. But if you think about these things, a lot does boil down. So I want to give a little bit example, just sort of how a bunch of different low-rank things do boil down to this, and then maybe you'll believe that a lot of other things almost do. So Halico had a nice, so this is extending some stuff Tigert had, and there was a range of scientific computing people who got implementations. And of course, they don't like the log factors, and for good reason. I mean, it's just not a way that they'd implement things. And they said, how do these things perform in practice? And they would describe it, the typical use case there is scientific computing. You're not doing matrix multiplication, but really you are under the hood. You're not doing least squares, but really you are under the hood. But you think this is a matrix, and the matrix is a discretization of a continuous differential operator. And you want typically, medium to high precision because you're solving a PDE, you're solving a climate model, you're solving some scientific. So there's been a lot of attention in geophysics and geosciences using these methods. And so that's sort of one. And are they asking a very similar question or a different question? So the way they describe it is the following. I have a matrix A. It's, both dimensions are large. It's not rectangular. And I specify a target rank, and then I don't say k log k over epsilon. I specify an oversampling parameter p that's 5. And I want to sample k plus 5 dimensions. And so I want to get factors u sigma v transpose that approximate A in some sense. So they typically are thinking low numerical rank, meaning 50 vectors gives them machine precision. So there's a difference there. Most data applications, 1,000 vectors gives you 50% of the Frobenius mass, which means things are very different. So they would say draw an n by k plus p Gaussian random matrix. Form the n by k plus p sample matrix Y, which is A times omega, which is your pi. Compute an orthonormal basis for that. Form a small matrix B is equal to Q transpose A. Factor the small matrix into U hat sigma V transpose, and then form U is equal to Q U hat. So if you know numerical analysis, you're probably familiar with that. Otherwise, it's not clear what one step or the other might be doing. You can prove bounds of the following form. So A minus the projection onto the columns this is the residual Frobenius mass, and it's 1 plus something of the form k over p. And in spectral norm, it's something having to do with the best rank k spectral norm plus something else. This is a Frobenius norm. So it's best rank k times a little multiplicative factor plus something else that's large. So how does this relate to what we were talking about, and what's sort of the underlying structural result here?
P equals 1 looks a bit dangerous, eh?
P equals 1 looks a bit dangerous. What they would suggest is 5 or 10. I don't know what they'd say, but the code they'd have would be 5 or 10. The probability, so here we're doing a low rank thing, and if you keep a few extra dimensions, which we didn't have in the least squares case, results get much better if you keep a few extra dimensions, but not 1. They'd say 5 or 10. But yeah.
I think you can actually get p equals, you can get a truly ranked k, but you don't have to have a few extra dimensions.
This is what they'd say.
This is what they said, but there is
Meaning you go to their paper, this is what they say. How do you relate it back to other things? And so
you can slightly change the analysis, I think, to get a ranked k.
So if they change the analysis, that may or may not be good for their use case. So the question is, what question are you asking? What question should we be asking?
Whatever
It
the
depends.
answer, it depends is. Yeah.
Right. So in a sense, I'm just describing a history, and they would do this thing and make a big deal about how it sounded different. They would, you would say, oh, you can change this and ask this other thing. They would say, yeah, but this other thing you did, we could change it and ask it our way. I'm just trying to say, yeah, what's sort of similar. But what's the connection between this and everything we've been talking about? And to highlight that, I'll say, how would you prove a structural result like that? A seemingly very different question is CUR, you heard the other day, or CSSP, the column subset selection problem. So I have a big matrix. Give me the k columns that are best. That's intractable for any notion of best. So give me the k plus p, or k plus 10, or k log k, and there's a range of ways to quantify that. But I want the best columns. So what, if anything, does that have to do with bounds of this form? It seems like a very different problem, but it is. So under the hood, they're going to be very similar. So this is So I showed you before a structural result that underlied, the 99% case as long as you're going to be a little bit cavalier about log-log factors. This is the similar thing for low-rank approximation. And this was first highlighted by Boutsidis in the column subset selection, but it's used as sort of the basis for a lot of the numerical analysis methods. So A minus the projection onto A, is that rank K or not? And so that's a second order bit, so there could be slight differences here. For what norm? Spectral, Frobenius, trace. So basically it holds for any unitarily invariant norm, and then it bifurcates depending on what you have, because you don't have matrix multiplication results for all of them. Is better than best rank K plus this. So what is this form? This is top K singular vectors perpendicular, meaning the bottom n minus K singular vectors, times best rank K times the complement of the best rank K. What is best rank K times the complement of the best rank K?
0.
0. I want to say that best rank K times complement of best rank K is roughly 0. So if you have this result, this is a deterministic statement. You could ask for an a priori bound, an a posteriori bound, subset selections, do random rotations, do Nystrom. Nystrom, you want to preserve symmetry and positive definiteness. There's a slight tweak on those properties, but it's a first order similar. Given the structure result, a wide range of sort of low rank approximations will follow. So this is a basic structure result that extends, and a special case of this is the least squares, but this is a more general thing because of the low rank space. So this is what we'll cover in the next sort of half hour. So this is sort of the basics, and you can use it in a lot of different ways, and I'll highlight a few ways that are ways that other people this week aren't going to be talking about in the next hour. So some of these things you heard from some of the other speakers, and I'll highlight a few that other people aren't going to be talking about in the next hour.
Questions for Michael?
So this low-rank approximation, doesn't that fall out from the matrix multiplication stuff you have? Multiplying A by an identity, right?
Yeah, so, I mean, this will reduce to least squares, which will reduce to matrix multiplication.
One slide back. So wouldn't that be similar to essentially multiplying A by an identity? And what's the difference here?
This is a projection.
So that's the only thing. If I only care about the outcome being rank K or rank P here, then can I just use one of those SS transpose instead of Q and still?
Yeah, this is the question they'd ask. They would describe it differently, and they would talk about Gaussian-based projections. And the structural result to justify this is the one on the next slide. With that structural result, you could do what you're talking about. Change the projection. As long as you satisfied those conditions, you get an analogous sort of statement. Yeah.
Okay, let's thank Michael again.